Well, welcome everyone. Thank you for joining us for today's Friday Happy Math Hour. Hope you guys are all doing well. As you can tell, we are reviewing for our first exam. If you are here, you are taking a Math 1324 class, and it's for the summer one. As you can see, it's pretty intense, right? We have to cover a lot of stuff in just 5 weeks. What we normally cover in 5 months, we have to cover in 5 weeks. So let's go ahead and get started. Um, and again, this review is just a quick review on some major topics that you've covered in the 1324. So let's go ahead and get started. So we have this question. Write equations of the lines through the given point that are parallel to and perpendicular to the given line. So we have a line here that they wrote in general form, which is the 8x minus 2y equals 3. So my two variables are this x and y, and my constants are the 8, -2, and 3. So what I want to do is to determine whether two lines are parallel or perpendicular. The deciding factor is its slope. If we have similar slopes, then that means that the lines are parallel. If we have opposite, or what I think opposite slopes, or slopes that are a difference of a -1, then that means that they are perpendicular slopes. So what I'm going to do is I'm going to use, what I'm going to do first is have this equation, 8x minus 2y equals 3, that it's in general form, and I'm going to go ahead and convert it into its slope-intercept form, which is in the form y is equal to mx plus b. And having it in that form, it allows me to see what the slope of that line is. So let's go ahead and start with that. So I'm going to solve for y, and when I do that, I have y is equal to 4x minus 3 half. Now, just to review, this equation now is in slope-intercept form, where it's in the form y is equal to mx plus b, where the 4 is my slope, m, and this -3 half is my value b, which represents my y-intercept. Now, in this problem, I am not interested in the y-intercept. All I'm interested in is in the slope, because two slopes that have the same two lines that have the same slope but different y-intercepts, that means that that they are parallel. So the equation that I need to come up with that is parallel to this line has to have a slope of 4, and I put it here in red. Now, they want me to do something else. They want me, the equation that I have to come up with has to go through this given line, through the 0.81. So now what I'm going to use is another form of the equation of a line, which is called the point slope formula. And the point slope formula is given here. Y minus y1 is equal to m times x minus x1, where again, m is your slope, and x1 and y1 is the point that you want to go through. Okay, so we have everything in order for us to get our answer. Our slope is 4 for our parallel. The point that we want to go through is this x1, y1 point. So let's go ahead and plug them in. And when we plug them in, we substitute the values. Okay, we have y minus 1 is equal to 4 times x minus a. The first thing that we're going to do is we're going to distribute that 4 both to the x and to the minus 8. Okay, so I'm going to get y minus 1 is equal to 4x minus 32. Then I'm going to subtract 1 on both, I'm sorry, add 1 on both sides. And when I do this, this is going to give me, oops, this is going to give me y is equal to 4x minus 31. Okay, so the equation of the line that is parallel to this one, as you can see, they both have a slope of 4, but they have different y-intercepts. This means that these two lines are parallel. All right, now let's do the perpendicular equation. So to find the perpendicular equation, again, I want to get what I call the negative slope, or when you multiply the slope with its negative, your value is -1. So if I multiply 4 times a -1 over 4, I get a value of -1. That means that these two are opposites of each other. Okay, and one way that I help my students get the perpendicular slope is I say that since these two are opposites, there are opposites in every way. Since my parallel slope is positive, my perpendicular slope has to be negative. Opposite of 4, if I again, if we know what slope is, which is rise over run, right? It's a fraction, and I can convert this 4 into a fraction, which would be 4 over 1. If I take the reciprocal of that, the opposite of that fraction, it's going to give me this 1 over 4. Again, so then again, it becomes the same process to get that perpendicular equation. I just substitute in the values. So when I substitute in the values again, I'm going to distribute first the negative 1/4 to the x and to the minus 8. And when I do that, I'm going to get a minus 1/4 x plus 2. Then I'm going to add 1 on both sides again as I did before. And I have now what's my perpendicular equation. This equation, y is equal to negative 1 over 4x plus 3, is perpendicular to the given equation with the 8x minus 2y equals 3 because of its slope. Okay. All right. Let's look at a question that involves um, a linear application. Okay, so they give us this information. We have a fixed cost on a certain product, which is $850. We have a marginal cost per item, which is $15, and the items individually sell for $30. And they want us to find the following: find the cost function, find the revenue function, find the profit function, find the profit on 108 items, and find the break even point. Um, all right, let's go ahead and start with this first one. A, find the cost function. So again, what we're going to do is we're going to assume that the following has a linear cost function. Okay, so again, just as the example that I just did before, what I'm going to do, a linear cost function is given by the equation y is equal to mx plus b. This is my linear form, but I want a function now. So the function format for this, or to build it first, let's get all the variables that we need. Okay, so when we see the word marginal cost refers to your slope. Okay, and in this case, the slope, the variable that we use for slope is our m. All right, now our fixed cost, when how it applies to our linear function, it refers to our y-intercept, our b value. So then I can put all this together, and we like to give names to our functions. Okay, so the name of this function, they wanted me to come up with the cost function, so we label it as a capital letter C of x. This is how we read this: C of x is equal to 15x plus 850. This is would be represented my cost function based on this information that I have here. Okay, let's do B, the revenue of a function. Okay, when we're talking about revenue, revenue refers to how much money a company makes based on the product they're selling. So the definition of revenue, okay, I need to come up with a function. So I'm going to call this R of X is equal to price times quantity. That's the definition of revenue. Price times quantity. Okay, so in my particular problem, to come up with the revenue function, I see that the price of the items that they're selling is $30. So $30 times a given quantity, and I'm going to use the variable x, gives me the revenue function. Rx equals 30x. This would represent the revenue. So just as an example, so if the company sells items, let's say that they're t-shirts or pants or whatever you want to think that they're selling, okay? So if they sell 2 pants, um, their what the company will make is $60, right? How did I come up with that money? Well, that's 30 times the quantity. They sold two. 30 times 2 is that $60. Yes? Okay, let's keep on going. It's asking us to find the profit function. So the profit function, as most of you know, is how much extra money the company makes um, after they had all their fixed cost, all their labor, and all the material that they used, that they spent to make the product. All that money extra is what's called our profit function, or our profit, right? So to come up with the profit function, we have this formula. First, we label it as P of X. Okay, this is going to indicate that we're dealing with a function. And the formula or the definition for profit is revenue minus cost. So for instance, the amount of money that a company made minus whatever it cost to make that item is that money left over, that extra money. That is our profit. Okay, so we have our revenue function, which is 30x. We're going to subtract that with our cost function, which is 15x plus 850. And if you notice, I had to put a parenthesis here because I'm dealing with a polynomial, right? We have two terms here. So this subtraction has to be distributed, just like before, to both of these terms. Okay, so then this is going to give me the profit, P of x is equal to 30x. A negative with a positive is a negative 15x. A negative times a positive gives me a negative 850. Okay. Now also just keep in mind when you're dealing with these functions, I'm not putting in dollar signs. Okay. The dollar signs is just to see what I'm dealing with, but do not put them in on your formula. If you put these value, the dollar signs in the computer is going to mark them wrong. Okay. We just want the values and numbers. Okay. So we see that we have two like terms, so we're going to combine those two. 30x minus 15x is going to give me my 15x minus 850. So if we see here, the profit is also a linear function, and it's in slope-intercept form, and the profit function is given by this. Capital letter P of x is equal to 15x minus 850. Okay, all right. Now they want us to find the profit on 108 items. So I already have the formula or the function in order to calculate the profit based on the number of items sold, right? So they want me to find the profit on 800 items sold. So what I'm going to do is I'm going to evaluate the profit function for the value 108. So here in dx, I'm going to plug in 108 to my function, which is 15x minus 850. So I'm going to evaluate this function. And to evaluate functions is everywhere you see x, you're going to plug in this value 108. Okay, so then I'm going to have p of 108 is equal to 15 times 108 minus 850. Okay, so when I do this, 15 times 108 minus 850, I get 770. Okay, but that's the value. But we always want to know what is this answer? What does this answer relate to? Well, this is money, right? This is the extra money that we are making by selling 108 items. So the answer is now we put in the dollar amounts to tell what we're dealing with. That we're not dealing with clothes, we're not dealing with an item, that this profit is giving us a value of money. So the profit for selling 108 items is $770. Okay. All right. And then we have the last point here. Um, Find the break-even points. So the break-even points means that the company doesn't either lose money or make money, that the money they invested to make whatever product it was, uh, they got it back with the sales. They didn't make any money, they just broke even, right? They didn't lose or make money. So the definition or formula to find the break even point or points is this. You take your profit function and you set it equal to 0. Okay. So I have my profit function. My profit function again is P of X is equal to P of X minus 850. And I'm going to set this function equal to 0. So to find the number of items sold that's going to make me break even, that's going to make me get back my money that I invested, I am going to solve for x. Okay, so the first thing that I do is I would add 850 on both sides. 0 plus 850 is just 850. To solve for x, I'm going to divide by 15 on both sides. And when I divide by 15 on both sides, this is going to give me x is equal to 56.6666 repeating, and I just rounded to one decimal point. So just be very careful on how many decimal places your homework wants you to give an answer to. But in this case, again, I'm just going to round it to the nearest whole number. So the break-even point, there was only one point because it's a line that is giving me my my break-even point is 57 items sold. Okay, so I had to sell 57 items in order for me to not lose any money, but at the same time not gain any money. Okay, all right. So let's move on to some fundamental stuff again. So This problem says determine whether the equation represents y as a function. So I started talking about functions for this class, but let's um, look into more detail as looking at functions. Okay, so I have these three equations. Y is equal to x plus 4. Hopefully by now, again, since we've been going through this, you recognize this first one is a line, and it's in slope-intercept form, right? So here, we know that if we would draw the line, it would represent a function. Now, how do we um, know that a graph is a representation of a function? So one way to determine that we're looking at a function is by performing a test. And the test that we're going to perform is called the imaginary vertical line test, right? That says that if you do an imaginary vertical line and your imaginary vertical line only crosses our graph only once, then that means that this is a function. Now, the definition of a function is that for every x value, it corresponds to only one y value. And that's what this imaginary vertical line is doing, that you're checking that every x value only corresponds to one y value. So it's very easy to see that this line, it is a function. Now the second one, they have a quadratic. And if we were to graph this equation here, the representation of this equation is this U-shaped graph, which is called a parabola. But then again, if I do my vertical line test, imaginary vertical line, I am going to see that my vertical line will cross my graph only once. So hence, this is also a function because it passes my vertical line test. All right, now let's look at this next equation. Okay, we dealt with a library of functions in this class. We can see that this equation is our square root function or a square root equation. And if I were to draw this, the graph of this equation is like this, right? This is just line starts at 4 and it shoots up, right? So again, if I do my vertical line test, it's going to pass. So then this is also a function. Um, now, let's look at this next example. Y is equal to x cubed minus 1. We went over this. It's an equation of a cubic equation or a cubic function. If we would do the graph, our graph looks like this. And again, if I perform my vertical line test, I will see that every x value only corresponds to one y value. So the answer is yes, this is also a function. Now, what about this one? Now, this one has y squared is equal to x plus 4. Okay, so if I were just to solve for the y, just so it to be um, how I've done my other problems before, okay, if I were to graph this, okay, I would see that I have this. I have a parabola, but it's on its side, right? And if I would do my vertical line test, I would see that my graph would fail. That just as an example, my x value is 0. For my x value is 0, sometimes I would have a positive 2, and sometimes I'm going to get a negative 2. That cannot happen. I cannot have two values for an input. So again, the definition of a function is that for every input, meaning for every x value, it only corresponds to only one y value. Okay? All right. So let's look at these functions and some of the transformations on functions. So on this particular example, they say use the graph of f of x equals x square root of x to write an equation for the function that's represented here. So I know that the square root of x, again, when we went through our library of functions, we know that square root of x starts at the origin and looks like this. But if we see here, this graph has the same shape, but it's at a different location. It went through some transformations. And what we can see is that, again, this is my what we call our parent function, okay, or our basic function. So this is where this graph came from this graph. But I see that this graph, let's look at first our what's called our horizontal shift. I know that this graph moved 2 units to the left. And the way I represent that this graph moves 2 units to the left is by this notation, x plus 2. Okay, so again, if you think about it, if I'm gonna move any graph left or right, the axis on which you are traveling on is the x-axis. So if I want to move left or right, I need to do something to the x variable. Now you might say to yourself, but if I'm moving to the left, why is it a +2? Think about the intercepts, right? If I wanted to find the x-intercept on this, and so to find the x-intercept, I would have to set my y equal to 0 and solve for x. So if you see here, if I had to solve for x, once I get rid of the square root, I need to move that 2 to the other side. And to move the 2 to the other side, I would have to subtract 2 on both sides. And this would give me x is equal to -2. That is its x-intercept. That's why we are going to move the graph to the left. Okay, but that's it. That wasn't its only transformation. We had a horizontal shift and moved to the left, but you see here, this graph also went down, right? So if you see here, it went down 8 units. It went from the 0 down to the -8. So how do we represent that transformation? It's called a vertical transformation. And again, we're not affecting x, so it's outside our radical. It's by itself. So for instance, think about it. If we would eliminate this first part here, the square root of x plus 2, and are left only with f of x is equal to -8, remember, y was f of x replaced the variable of y. So that's telling me that y is equal to -8. Hence, it's going to produce our vertical shift. So the equation represented on this first one is this. F of x is equal to the square root of x plus 2 minus 8. And this is how we would did transformations. Okay. Um, let's look at another one. Okay. And just to keep on practicing on the same function, the square root of x, this one looks a little bit different than what we're used to, right? This is our main function or our parent function. The f of x is equal to square root of x, but it looks like it's a little weird, right? Well, let's look at what happened on this one. If you see here, if we were to multiply a negative to our regular function square root of x, what we would have is this reflection. This is a reflection on our x-axis. Instead of looking at all as an answer all the positive values, which is what this one gives us, if we multiply all those positive answers by a negative, what we're going to get is all negative answers, and it's going to produce this graph now in green. Okay, so now it kind of has the same shape, but it's like pointing the opposite direction. So to get that opposite direction, what we have to do now is instead of looking at all the x values from the beginning, we want to look at all the x values. We want to go the opposite direction. Instead of moving forward, we want to go backwards, right? So to do that, we're going to multiply a negative to the x inside the radical, and that's now going to give us our shape that we want. See, now we have a similar shape. Now it just comes down to some basic horizontal and vertical transformations. So let's start with the horizontal again. Now that we have the same direction and shape, we see that this graph got moved 2 units to the right. So how are we going to represent those 2 units to the right? By subtracting 2 to our x. That -2 means that I'm moving my graph 2 units to the right. Okay. Now then we also had a vertical transformation or a vertical shift. My graph here from the beginning, it got shifted down 5 units down. So how do I represent that shift 5 units down? Is I'm going to go outside the radical, and it's going to be the -5. That directly affects my y value, and hence now I have my equation that represent the transformations on this graph. Okay. All right. So let's move into polynomial functions. Well, what is a polynomial? Okay. So the name kind of says it all, and you guys are familiar with this. Okay. Poly is a prefix term that means many. Yes. Nomial is a Latin word for number. So many numbers, or in our case, we are going to be looking at polynomials with many terms. Okay, so in this particular one, what makes a polynomial function or a polynomial? Well, first is that it has a continuous graph. A polynomial is not going to have breaks, like my second example. If I have breaks on my graph, then that graph is not a representation of a polynomial, okay? So like back in high school, they told you to write a polynomial on a graph is like if you can draw the graph without lifting your pencil, right? It's a smooth curves. You never lift your pencil up, okay? that's what's gonna make it a polynomial. What also makes a polynomial is that it doesn't have any sharp turns. Again, like this first example here, I have many terms, but all the terms, all these peaks and valleys, like your book explains, they're smooth, right? This is a polynomial. But if I look at this one here, and this is an example of one of our library of functions that we saw, this is our absolute graph, right? Our absolute graph has a sharp turn. So this graph is not a graph of a polynomial. It can be a function, but it's not a polynomial. Okay. All right. So based on this information on polynomials, okay, you're asked to graph polynomials in this class, and the way to graph polynomials, you have to get several things. You have to understand what's happening with graphs. So first, one of the things you know is that we want to find the intercepts of the graph. So that's the first thing, the solutions or the zeros of the graph. So whenever you hear these words, find the zeros of the graph, find the solutions of the graph, or find the intercepts, they all mean the same thing. And it's where in the graph is crossing the x-axis. So this is, for instance, this polynomial here, this first one, it's given to me as x minus 2, x plus 1, x minus 4. It's already factored out to me, so we love it because it's easy to see all of the zeros that this polynomial has. It has zeros at x equals 2, x equals negative 1, x equals 4. Okay, so when I'm connecting these dots, again, we do smooth curves. Okay, um, I want to bring out like this middle example here. Okay, on this middle example, if I were to factor this polynomial, okay, then I would want to factor it by grouping. Okay, on this particular problem, I have 4 terms. Okay, I would cut it in half and factor each one. And when I would do that, I would find my zeros, and I would have zeros at -2, at +2, and at -2. So when I see this, that I have two answers that are the same value. What this is referring to in our graph is that our graph is touching. So whenever you see a graph that our graph touches, that means that this zero here at -2, 0 counts for 2. There's 2 zeros there, okay? And the way we explain this is when we're evaluating graphs, okay? If you remember, when we're evaluating graphs, we evaluate this graph increasing and decreasing, right? This graph is increasing from -infinity to -2, and then it's decreasing from -2 to 0. So that -2 plays 2 parts, the increasing part and the decreasing part. So hence, that's why it's called a double zero, because it's part of 2 parts of the graph. Okay. Now on this one, when we only have one individual value, that means that the graph crossed the x-axis. So in this case, we only have one +2, so that means that our graph crossed 2. Again, similarly with this last example, okay? So we have x to the fourth minus 4x squared, okay? And we would find the zeros of this, okay? And then on your homework, they're going to give you the zeros, or they're going to factor it out, where you just have to solve it, okay? Um, we have zeros at 0, 2, -2, and 0. Oh, in this case here, we have a double zero. So and you can see it on the graph here. The graph on this 0 is only going to touch and then turn around. Okay. Now, how do we find the direction? Again, to do the direction, you do a table, find values to the left and to the right of 0 in order to get your smooth curves and find the graphs on these. Okay. All right, let's move to the quadratic section. Okay, the standard form of a quadratic section and graphing is this. Okay, we were given 2 equations. The first one here, the ax squared plus bx plus c, we call that our general form. But before we even dealt with the quadratics, we were dealing with functions that you still didn't know, but we were dealing them in this format where they were a is equal to, or f of x is equal to a times x minus h squared plus k. This one we like to call it, it's called our vertex form, or some books call it the standard form. Okay. Now, the quadratic function, uh, the graph that it reproduces is called a parabola. Again, it's this U-shaped graph. The point here where it goes from decreasing to increasing is its vertex. The vertex here is called the origin, right? The 0, 0 that's between this two number lines, the vertical line, which is our x-axis, and the horizontal line, which is our y-axis. This is point here is called the origin. Okay. Now the graph that I have here, I like to call it the parent function or the parent quadratic function. Okay. This is the graph that will allow me to recognize all of the children. And that's why I like that name parent, because when graphing this, okay, if I know that my parabola or my graph came from a quadratic, I know it's this parabola shape or U-shaped graph. Okay. And if you see, this quadratic is an example of a polynomial function. Its degree is 2. And again, to review degree, the degree of a polynomial is the highest exponent that a function has. All right? Okay, so here, the quadratic in general form is ax squared plus bx plus c. This f of x squared, again, is my parent, is this U shape. But if I look at this graph now, minus x squared, okay, this one, again, we covered this already right now before. This will create a reflection on my x-axis. It's just I only want to look at the negative values of my graph, okay? All right, so again, here, if I'm looking at my general form here, the a value, if that a value is positive, that's a greater than 0, that means that my parabola is going to be opening upward. If my a value is negative or a is less than 0, I know that is going to be pointing downward, okay? So again, this value is important. There's this value here is called my vertex, and if it's in standard form, it's easy to see. It's CH and K. Now, your book also gives you a formula to find the vertex. If in case that they're not giving it to you in standard form and they give you the equation in general form, you would use this formula to find the vertex. The vertex can be found by getting negative b divided by 2a. That will give you your x value. And to get your y value, you just get this answer and you plug it back into the function to get your y value. Okay. All right. So again, these are the two forms of a quadratic that you can see in order to graph. So it's very important, as you can see, it's very easy that if they give us a quadratic in standard form, it's very easy to see what our vertex is. It's just the h and k value. So we can do what's something that's called completing the square in order to convert a quadratic that is in general form into its standard form. And completing the square is a fundamental factoring procedure, okay? So the way we complete the square is this. When they're giving us a trinomial, we have a three terms function. What we want to do is we're going to take half of b and we're going to square that value. Okay, so and once we square that value is the c value that is going to make my function or quadratic function a perfect square, and that's what completing the square means. We want to have a perfect square. All right, so once I have this, my fourth step is again once I've taken my b divided taking the half of it and squared, I'm going to subtract it to any c value that was already there in the function, okay? Now, the last step is just to get my perfect square, giving me my h and k values. So let's go through a problem that better describes this process instead of me just giving it to you with variables. Let's do it with a real function. So let's say we have this function f of x is equal to x squared plus 2x plus 1. And I want to convert it into a standard form so I can identify its vertex. Okay, so again, here I need to know what my values are, a, b, and c. In this case, my a is 1, my b is 2, and my c is 1. Okay, so the first thing that I'm going to need to do in my first step is I'm going to grab my b, which is 2, and then I'm going to take half of that, right? So half of 2 is 1, and then I'm going to square that 1. So 1 squared is 1. right? So if I were to add 1, if c would be 1, then that means it's a perfect square. So in this problem, I already have that 1 there, so I don't want to add anything. I'm just, or I can add 0 here, and then I'm going through the motions because this one's a perfect square, but let me go through the motions of what you would do, okay? So you can't just add any numbers to a function because you can unbalance it, right? So what I'm going to do is I want a 1 there, so I'm going to do 1 minus 1, and the value of 1 minus 1 is 0. When you add 0 to something, you're not changing it. Now, again, I didn't have to do that because I already had a 1 there, but I'm just going through the process on how to complete the square, right? So when I do the 1 minus 1 and add them, again, I get 0, and then when I simplify that, okay, I'm only going to end up with the x squared plus 2x plus 1, okay? This now becomes a perfect square. This x squared plus 2x plus 1 can be rewritten as x plus 1 times x plus 1, okay? That's a perfect square. That's what perfect square means, that I have two terms that are identical that are being multiplied together. Now, again, if I would do FOIL to multiply these two products, what I have here is this, x plus 1 squared. And you see here, now I can see what my vertex is. There is no value here. The plus 0 means that I don't have an h value, but I do have a k value. This graph got shifted 1 unit to the left. And again, remember from finding our x-intercepts, it's a plus 1. The vertex is at minus 1, 0. Okay. All right, let's do another one. Let's do this one. F of x is equal to 5x squared plus 15x minus 5. Okay, let's complete the square so we can put it into its general form. And again, what I did on this one is I'm just putting in the formulas that I'm doing to calculate my c. Um, so here, again, what I want to do first is I want to factor out an a. So since this trinomial have a common factor of a 5, that's what I'll do first. I'm going to factor out a 5, leaving me with just a for 1. So then I take half of 3. Um, sorry, half of 15 is, actually, I have a typo here. Oh, it's all down here. I did it again. These two are not correct. It's down here. It's half of 3 is 2. And then when I square it, I get, you know what? I'm gonna forward this one because I do have a typo. This should have been 3 squared, not 15 squared. Okay. Um, I believe my answer is correct. It's just the values that I put here. Okay. But let me just go ahead and just finish the process again. Whatever squared value that I have, I'm gonna add it to the value that I already had here, which was that minus 5. And when I add those two values together, it's gonna get me this point, which is going to give me now my vertex. My vertex is, again, this is the plus 3 halves. I needed to shift my graph 3 half units to the left, so that's why it's a minus 3 halves. And this value stays as is. It's a minus 65 over 4. And there is my vertex, okay? All right, so methods for solving quadratic functions. There's several methods that you can use. You can use what's called your square root property. You can also use you can factor the trinomial, or you can use what's called the quadratic formula. Now, when using the quadratic formula, this method will always work to find the solutions. Now, again, just to remind all of you, the quadratic formula is to solve for the x-intercepts of a graph, of the parabola, okay? So let me give you examples of using the square root property. So let's say that I have a simple quadratic like this, x squared minus 4. I can use my square root property by setting this equal to 0 and then just solving for x, okay? So I add 4 on both sides, take the square root of both sides, and this gives me my two answers. X is equal to plus or minus 2. Or like this other little bit more complicated example, I want to set the quadratic equal to 0 and then solve for x. I add 27 on both sides, divide by 3 on both sides, take the square root of both sides, add 4 on both sides, and you see that I get x equals 7, and x equals 1. So these are ways to just use fundamental algebra to solve for the x-intercepts given a quadratic, okay? But keep in mind, sometimes these methods won't work, or especially with factoring. I love factoring. I think factoring is the easiest way to factor out a quadratic or a trinomial, but not all polynomials or functions are factorable. Like in this particular one, it is. X squared minus 6, x squared minus x minus 6 can be factored into x minus 3 times x plus 2. So it's easy for me to see what the intercepts of this quadratic are. X is equal to 3 and x is equal to negative 2. These are the two values that would make my polynomial equal to 0. If I plug in a positive 3 here, I get 0. If I plug in a negative 2 here, I get 0. Okay, but again, sometimes these don't work, and sometimes we have to use what's called our quadratic formula. And the quadratic formula is given by this: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, handful, right, or mouthful, right? So you need to know what your a, b, and c are. In this case, in this particular problem, my a is 1, my b is negative 2, and my c is negative 8. I just plug in those points, solve and simplify. And again, using the quadratic, I get that the x-intercepts are at x equals 4 and x equals negative 2. So it can be quite a work to do the quadratic formula, but it's one that will always work, okay? All right, so we come to our last topic to review for your first exam in your 1324 class. So what we have here is um, a rational function, and for this, you may be asked to find the domain of the function. You're going to be asked to find certain details of this function. Okay, so first, let's start with the domain. Okay, so to find the domain of a rational function, again, we have to be careful. Some books call this the fraction function, right? So when we're dealing with a fraction, we never want to have a zero value in our denominator. If we ever have zero in our denominator, that produces an unsolvable problem. It does not exist. If we would divide by zero in our calculator is going to say error, cannot be done. Okay, so when we're dealing with these problems, we do not want zero to be a non-denominator. So we have a restriction on our domain. We cannot, when we say a restriction on domain, means that we cannot use or there's certain x values that we cannot use in our function because we would get an error. So to do that, if you don't see that, to find the domain of our function here, and if you don't see it, you would set the denominator equal to 0, right? So the x plus 3, you would want to set to 0, again, because we cannot have 0 for a fraction. So again, if you don't see it, we would set the denominator equal to 0, x plus 3, subtract 3 on both sides, and we would see that x is equal to 3, right? Or some of us would see it, that if x was a negative 3 plus 3, that would produce a 0. So on this particular function, we can use all x values for the function except for negative 3. So if I have the answers here as a multiple choice, the answer that I want is this last one, right? That my answer has to be all real numbers for x except for x equals negative 3, because if x would be negative 3, I would have an error, okay? So this is my restriction on this domain. I can use all values except for negative 3. Now, let's practice and review intercepts, okay? To find intercepts, to find an x-intercept, you set y equal to 0, and then you solve. So I'm using this equation to also practice one of the stuff that we went over like in chapter 2, right? Or in the beginning, the x-intercepts. So again, to this one, I'm going to find the x-intercepts by replacing y equal to 0, and then I'm going to solve for x. So the first thing I need to do is I need to multiply by x plus 3 on both sides. And when I do that, I get this statement: 0 is equal to 1. This is a false statement. This is not true. So by me getting a false statement, what this is telling me is that I do not have any x-intercept. So the answer that you would put here is does not exist, or there's none. Okay. Let's practice finding our y-intercepts. So again, to find our y-intercepts, you set x equal to 0, and then you would solve for y. Okay, just a review, f of x is a symbol that we gave to our equation to indicate that we're dealing with a function. So um, f of x to solve for y is we're really solving for this f of x at our input 0. So everywhere I see x, I'm going to plug in 0 and simplify. So 0 plus 3 is 3. So y is equal to 1 over third. Oh, sorry, 1 over 3, or 1/3, right? So our y-intercept as a value, as our input, is um, 0 for x, 1/3 for our y. Okay. Now, what is it? The other thing that we looked at when we looked at these rational functions. Okay, rational functions have what's called a vertical and horizontal asymptotes. These vertical and horizontal asymptotes are these imaginary lines where our graph does not cross or touch. Okay, so if we looked at our example, our problem that we have here, okay, or just to review, the way we represent asymptotes in a graph are by these dashed lines or dotted lines, right? So one way to find that our vertical asymptotes is our restriction on our domain. When we set our denominator equal to 0 and we solve it, what we get, our result of that, is our vertical asymptote. It's these imaginary vertical lines. And it makes sense that it's a vertical line because we're restricting our x. This value at value, let's say, for instance, if this value is 1, at 1, I cannot use 1, so hence I have an imaginary vertical line because everywhere x is 1, I cannot use, right? So going back to my example that I was working at, is what is the vertical asymptotes on this problem? And again, when we solved for the domain on this problem, set our denominator equal to 0, we discovered that x um, equals to -3 would give us an error, right? An undefined. So what this is, this x equals -3, is our definition of our vertical asymptote. This is the equation of the vertical asymptote. At x equals -3, we're going to have an imaginary vertical line, okay? So, and we will represent it like this as a dashed line. Okay. Now, again, on your homework, you don't have to do all this process. Most of your questions, depending on your instructor, they're just multiple choice. It's just you understanding what you're looking at. Okay. All right. So the next thing that we need to do in order to understand what the graph of our rational functions look like is to find our horizontal asymptote. Okay. Now, for our horizontal asymptote, there are several different cases that will determine what our horizontal asymptote is. And there's three cases I like to think of, or 3 points that will tell us, excuse me, what our asymptote is. So for this is the first one. Um, if the degree of our numerator is smaller than the degree of our denominator, then we will always have a horizontal asymptote at y equals 0. The second case is that if the degree of our numerator is equal to the degree of our denominator, then we're going to have a horizontal asymptote with a ratio or a fraction. And that value is given by the division of the leading coefficient of the numerator divided by the leading coefficient of the denominator. And that will give us what's called our horizontal asymptote. And then we have our third case, that if the degree of the numerator is larger or bigger than the degree of the denominator, then there exists no horizontal asymptote, okay? Now, let's go back to our problem. If we see here, in our problem, the degree of our numerator is smaller than the degree of the denominator. Now, let me write it here to show you, so maybe you can see it even better, and I should have put this on here, okay? Let me rewrite this polynomial or this function like this. X on top to the 0 value, and then we have on the bottom we have x plus 3 but let me write the exponent or the degree that this polynomial, this x has. Okay, so see here, x to the 0 power. Anything to the 0 power, the value is 1 here. And the degree of a polynomial is always the highest exponent that you see in that polynomial. So here, the value for the polynomial on top is 0, our numerator. Now on the bottom, I have a polynomial here, x to the first power. We never write the 1. When there's a 1, we know that there's only one x there. We don't have to tell the reader that there's one x, but there's a 1 here. So here it's clear to see that the degree of the numerator is 0, the degree of the denominator is 1. So here the degree of the numerator is smaller than the degree of the denominator, so hence I have a horizontal asymptote at y equals 0. And I represent that as a horizontal line. Opposite to a vertical asymptote is a horizontal asymptote, which is a horizontal line. So this is my two things that are restricting my graph. And again, if you remember from when we did our library, and again, if you remember from when we did our library of functions, oops, we can graph it, but again, to do an exact graph and to review, you want to go through these process. You want to find its intercepts. You want to find the vertical asymptote, the horizontal asymptote, and then you want to plot some additional points. Okay, so when I plot my intercepts, and based on the fact that I know what my problem looks like, and by plotting these additional points, okay, I get a graph. These are plotting these points. So the points that I used, my additional points that I used to graph was -2, 2, -4, and -5. Now, why did I pick these points? Again, I picked these points that are in reference to my values that or my restrictions that I have. Since I had a -3, I wanted to find a value to the right of this. And the reason why I used the -4 is because I want to use the value to the left of this, right? I just used 2 just to do an opposite number, and I use -5 just to look at a greater number of possibilities. So these are my points. I plug them in. Again, I plug them in based on if they're positive or negative on my Cartesian plane. And then I try to do a smooth curved line. Yes? So this is the graph of this function. Again, most of your problems for your homework, they're just multiple choice. It's just understanding what you're looking at, discovering your asymptotes, and doing these extra points, your intercepts and extra points to see what the graph of it's supposed to look like. Okay. All right, guys. So this concludes my presentation. Hopefully, this helps you review a little bit of some of the main concepts that you're going to see on your first exam for your Math 1324, excuse me. I wish you the best of luck. Some of you might be taking your exam today. Some of you, my classes, maybe taking it next week on Monday. Okay, so for all of you, I wish you good luck, study hard. We're going fast. Summer 1. We're already to our first exam. Thank you for joining me. Hope to see you again or next week. Goodbye.
Next week, we will have exam 2 review. Thank you so much, Professor Ruben Carrizales, for presenting today. And thank you to the audience for coming and being a wonderful audience. And we hope to see you again soon. Thank you.